So now that we finished the first round of coverage of Java threads, it's time to turn our attention to the other key part of Java concurrency, which are synchronizers. And in order to ease the transition from threading to synchronization, we're first going to take a brief tour through the Java memory model. So Java has something called a memory model. And if you take a look at the Java language specification, you'll see there's a whole big section on memory models. If you take a look at the link at the bottom of this page, you'll see a summary of the Java memory model. And basically what the Java memory model does is it defines the semantics of multi-threaded access to memory that's shared by multiple threads running within a process. So when I say shared memory here, I don't mean shared memory between separate processes on the same computer, but instead I mean the concept of having global memory or memory that's accessible by multiple threads within one process or one virtual machine instance. Now, one of the things that the memory model does is it describes what types of instruction reorderings are allowed in memory. And this at first may seem a little weird. Why would you want to reorder things? Well, the reason you want to be able to reorder things is to take better advantage of modern instruction sets that have pipeline caches and all kinds of clever optimizations that are done at the low level of the hardware. You may also want to reorder instructions by the just-in-time compiler or the Java compiler. There may be reasons to reorder things so that you get better efficiency with respect to caches, both instruction caches and data caches and so on and so forth. And so it's important to know what kinds of reorderings are legal and which ones are illegal. And I suppose I should really say it's important for the compiler writers to know these things. You as an end user can be only vaguely aware of this, but you do need to be aware that reordering can take place, because if you're not aware of that, then your program will do very strange things, especially when you run it in a multi-threaded context. So let's take a look at a simple example here. Let's assume that we have some variables, x and y, and we'll say they're ints, for lack of a better thing. They could be longs to or chars. And let's assume that they are accessible to thread 1 and thread 2. So we'll assume thread 1 starts up. We'll assume thread 2 starts up. Let's assume, for sake of argument, they both start up at the same time. And thread 1 says x equal 1, and thread 2 says y equal 1. And let's, again, assume that they do that at the same time. And then thread 1 says j equals y, and thread 2 says I equals x. And let's assume, for sake of argument, that j and I are local variables, local to the thread that they're being called in. Well, it can turn out, due to various caching effects, especially on modern multi-core processors, that I will have the value of 0 and j will also have the value of 0, even though x was set to 1 and y was set to 1 before j was set to y and I was set to x. And that's because modern multi-core processors often do a lot of caching, and those caches aren't necessarily flushed immediately unless you do something at the programming level to inform the underlying virtual machine or the execution environment that you want those caches to be flushed so that the memory is consistent between the different threads. So this is very important to understand this, and you'll get all kinds of weird problems if you don't understand this. Another set of considerations that the Java memory model says is what program outputs may occur in a correct implementation of the Java execution environment. And again, if you take a look at the specification for the Java language, you'll see some discussions of these kinds of things. So this is a variant that's very similar to what we saw before, where we're going to have x and y, which are variables that are shared between thread 1 and thread 2. And then you can see that R1 is set equal to x, and then y is set equal to R1, and R2 is set equal to y, and x is set equal to R2. And basically what the Java virtual machine specification says is you just can't have random values here. They have to be somehow related to what's going on. And so as a consequence, there's some things that can happen, but other things that can't. And again, this is all very low level and very sort of language lawyer type of stuff. In my experience, reading about the semantics of Java's memory model is about as much fun as watching paint dry. It's very boring. Now, if you really want to know all the details about this stuff, you can take a look at the frequently asked questions file that's down here at the bottom of the page and learn all these things. However, the good news is if you learn how to use Java synchronizers, things like the synchronized statements and synchronized methods, reentrant lock, reentrant read-write lock, condition objects, semaphores, atomics, barrier synchronizers, and so on, you don't have to know much about the Java memory model. You never have to go and read that horribly boring specification, and your code will work quite nicely. It's only if you start trying to do really clever things where you have to understand more about how the Java memory model works. And we will, in fact, talk later in the course about some clever techniques you can use where you do have to know how the Java memory model works in order to write code that will, in fact, do things like safe management of objects that are shared between threads. And we'll talk more about that later. So that's the end of the overview of the Java memory model. It's just something you need to be aware of. But the most important thing to be aware of from this whole discussion is if you don't use proper synchronization in your multi-threaded Java code, then any shared mutable state that is accessed and or updated by different threads in that process is likely to have very strange results that are not what you expect and not what you want. So the key point of all this is learn to use the synchronizers we're about to be covering, and most of the mysteries and subtleties in the Java memory model will just magically never affect you at all, which is a good thing.